So here you are, lying in the dark, maybe pulling the covers up a little, getting comfortable. And tonight, I want to take you somewhere genuinely strange. Somewhere so strange that the words we use to describe it almost stop making sense. I want to take you inside a black hole. Now, you have probably heard of black holes before. You know the basics. They are regions of space where gravity is so intense that nothing can escape, not even light. You have seen the images, maybe the famous one from the Event Horizon telescope, that glowing orange ring around a dark shadow. You have heard the phrases, event horizon, singularity, point of no return. And all of that is true, as far as it goes. But tonight we are going to go further than the surface-level story. Because inside a black hole, something happens that is so profoundly weird, so fundamentally reality-bending, that even physicists spent decades arguing about whether it could possibly be true. Inside a black hole, space and time switch places. Let that sit for a second. Space and time, the two most basic ingredients of your entire existence, the stage on which everything you have ever experienced has played out. They trade roles. The direction that was space becomes time. The direction that was time becomes space. And the consequences of that swap are absolutely wild. But I am getting ahead of myself. Let's start somewhere simpler. Let's start with the thing you are feeling right now, this very moment, as you lie there in your bed. Gravity. You can feel it, right? That gentle pull of the earth, pressing you down into the mattress. It is so constant, so familiar, that you barely notice it most of the time. It is just the background condition of your life. You wake up, your feet hit the floor, things fall when you drop them, water flows downhill, gravity. It is the most everyday force in the universe, and for a very long time, we thought we understood it pretty well. Isaac Newton, back in 1687, gave us a beautifully simple picture. Every object with mass attracts every other object with mass. The bigger the mass, the stronger the pull. The farther apart, the weaker it gets. Simple, clean. It explained the orbits of planets, the trajectories of cannonballs, the tides of the ocean. For more than 200 years, Newton's gravity was one of the great triumphs of human thought. But here is the thing. Newton himself knew something was off. See, Newton's gravity acted instantly. If the sun suddenly vanished, in Newton's picture, Earth would immediately fly off in a straight line. The gravitational signal traveled at infinite speed. Newton found this deeply troubling. He wrote about it in private letters. He called it an absurdity. But his equations worked so well, so beautifully well, that everyone just sort of accepted the weirdness and moved on. It took more than 2 centuries for someone to figure out what was really going on. That someone was Albert Einstein, and the answer he came up with, in 1915, did not just fix Newton's little problem about instantaneous action. It completely rebuilt our understanding of what space, time, and gravity actually are. And it is Einstein's picture, his general theory of relativity, that leads us directly to black holes and to this mind-bending idea that space and time can switch. So let me tell you what Einstein figured out. Einstein's great insight, the one that changed everything, was this. Gravity is not a force. It is not a pull. It is not some invisible rope stretching between masses. Gravity is the shape of space-time itself. Now, space-time. That is a word you have probably heard, and it can sound intimidating, like it belongs in a physics lecture. But the idea is actually pretty intuitive once you sit with it for a moment. You already know what space is. It is the 3 dimensions you move through every day, left and right, forward and back, up and down. You navigate space constantly. And you know what time is. It is the thing that keeps moving forward. Yesterday, today, tomorrow. The relentless tick of the clock. The thing you cannot stop. What Einstein realized, and this came first in his special theory of relativity in 1905, is that space and time are not separate things. They are woven together into a single four-dimensional fabric. Space-time. You exist in 4 dimensions right now. 3 of space, 1 of time. You are always moving through space-time, even when you think you are sitting perfectly still, because even when you are not moving through space, you are always moving through time. And here is the really beautiful part. In Einstein's picture, what we experience as gravity, that gentle pull you feel right now, pressing you into the mattress, is actually the curvature of this space-time fabric. Think of it like this. Imagine a large trampoline, stretched out flat. Now, place a bowling ball in the middle. What happens? The trampoline surface curves. It bends down around the bowling ball, creating a kind of, well, a depression. Now roll a marble across the trampoline. If you aim it just right, the marble does not fly in a straight line anymore. It curves around the bowling ball. It follows the curved surface. If the marble is going slowly enough, it spirals in toward the bowling ball. If it is going fast enough, it swings around and flies off in a different direction. That is gravity. Not a force pulling the marble toward the bowling ball, but the marble simply following the curved surface of the trampoline. The bowling ball warps the surface, and the marble responds to that warp. Now, the trampoline analogy has its limits. For one thing, a real trampoline is a 2-dimensional surface curving through 3-dimensional space, and what is really happening with gravity is that 4-dimensional space-time is curving in ways that are much harder to visualize. But the basic intuition is right. Mass tells space-time how to curve, and curved space-time tells mass how to move. That is general relativity in a single sentence. The physicist John Wheeler put it exactly that way, and it is one of the most elegant summaries in all of science. So here you are, lying in your bed, and the Earth beneath you, all 6 billion trillion kilograms of it, is curving the space-time around you. Your body wants to travel in a straight line through space-time, but because space-time is curved by the Earth's mass, a straight line through space-time leads down toward the center of the Earth. The mattress and the floor are pushing back against you, preventing you from following that curved path. And that push, that resistance, is what you feel as gravity. You are not being pulled down. You are being prevented from falling along the natural curve of space-time. That is a wild thing to realize, honestly, that the force you feel right now, pressing your back into the bed, is not gravity pulling you down. It is the bed pushing you up, away from the path space-time wants you to follow. If the floor disappeared and you were in free fall, you would feel weightless. You would feel nothing. Because free fall, falling along the curve of space-time, is the natural state. It is standing still on the surface of the Earth that requires force. Astronauts floating in the International Space Station are not experiencing zero gravity. They are in free fall. They are falling along the curvature of space-time around the Earth, just like the Moon is, just like every orbiting satellite is. They feel weightless because nothing is pushing them off their natural path. Okay, so that is the background. Gravity is not a force. It is curved space-time. Mass curves the fabric of the universe, and everything, including light, follows those curves. This picture, Einstein's picture, is one of the most thoroughly tested theories in all of science. GPS satellites have to account for it. Without general relativity corrections, your phone's navigation would be off by kilometers within a day. The theory works. It works phenomenally well. But Einstein's equations also predict something extraordinary. something Einstein himself did not want to believe was possible. They predict that if you take enough mass and squeeze it into a small enough space, space-time does not just curve a little. It does not just make a gentle dip like the bowling ball on the trampoline. It curves so extremely, so drastically, that it forms a kind of bottomless pit, a region where space-time is warped so intensely that nothing, absolutely nothing, can climb back out. That is a black hole. And the story of how we got from Einstein's elegant equations to the terrifying reality of black holes, that is a story worth telling, because it did not happen quickly, and it did not happen cleanly. It involved some of the most brilliant minds of the 20th century, some of them working in the most extraordinary circumstances you could imagine. Let me tell you about Karl Schwarzschild. It is 1915. The First World War is raging across Europe. Schwarzschild is a German physicist and astronomer, one of the finest minds of his generation. He is also 41 years old and serving on the Eastern Front, calculating artillery trajectories for the German army. He is stationed in Russia, in freezing conditions, surrounded by the chaos and misery of trench warfare. And in the trenches, between calculations for how to aim cannons, Karl Schwarzschild does something remarkable. He gets his hands on Einstein's newly published paper on general relativity. Einstein has only just presented his field equations to the Prussian Academy of Sciences in November of 1915. The ink is barely dry, and here is Schwarzschild, on the front lines of a war, reading these dense, complex equations by candlelight, and he solves them, not approximately, not in some simplified special case. He finds an exact solution to Einstein's field equations, describing the space-time geometry around a perfectly spherical, non-rotating mass. It is the first exact solution anyone has found. Einstein himself had only managed approximate solutions. Schwarzschild, sitting in the trenches, does what Einstein could not. He writes up the solution and mails it to Einstein. Einstein presents it to the Prussian Academy in January of 1916. He is reportedly amazed, both by the elegance of the solution and by the circumstances under which it was derived. In a letter to Schwarzschild, Einstein writes that he had not expected anyone to find an exact solution so quickly, and he is delighted by the result. But Schwarzschild's solution contains something troubling, something that would haunt physics for the next 50 years. In Schwarzschild's solution, there is a special radius, a distance from the center of the mass where something very peculiar happens to the mathematics. At this radius, some of the terms in the equations blow up. They go to infinity. The math seems to break. This radius depends only on the mass of the object. For the Sun, it works out to about 3 kilometers. For the Earth, it is about 9 millimeters, less than a centimeter. Now, the Sun is actually about 700,000 kilometers in radius, and the Earth is about 6,400 kilometers. So for ordinary objects, this special radius is deep inside the object itself, well below the surface, and Schwarzschild's solution, which describes the empty space outside a mass, does not actually apply there. But the question lingered, what if you could compress all that mass down below that special radius? What if you could squeeze the entire Sun into a sphere 3 kilometers across? What would happen? Schwarzschild himself never got to explore this question. Tragically, he developed a painful autoimmune disease while serving on the front. He was evacuated from the front lines, but his condition worsened rapidly. Karl Schwarzschild died in May of 1916, just a few months after his groundbreaking paper was published. He was 42 years old. But the question he left behind, the mystery lurking inside his own equations, would keep physicists awake for decades. That special radius, the one where the math seems to break, is what we now call the Schwarzschild radius. And the surface at that radius, the invisible boundary surrounding any sufficiently compressed mass, is what we now call the event horizon. For a long time, most physicists, Einstein included, believed the event horizon was just a mathematical artifact, a problem with the coordinates Schwarzschild had chosen, not a real physical thing. Einstein wrote a paper in 1939 arguing that stars could never collapse down to this radius. Nature, he believed, would find a way to prevent it. The event horizon was just a mathematical curiosity, nothing to worry about. Einstein was wrong. But to understand why he was wrong, and to understand what really happens at the event horizon, and especially to understand this wild claim that space and time switch places inside a black hole, we need to talk about something crucial. We need to talk about light cones. And I promise, this is going to be one of those things that, once you see it, changes the way you think about everything. So, light cones. This is one of those concepts that sounds technical, but it is really just a way of thinking about what is possible and what is not, about where you can go and where you cannot, about the structure of cause and effect itself. Let's start with something simple. Right now, you are lying in bed, at a particular point in space and a particular moment in time. You are here, and it is now. From this moment, there are things you could do. You could get up and walk to the kitchen. You could throw a ball across the room. You could shine a flashlight at the wall. All of these are possible futures for you. But there are also things you absolutely cannot do. You cannot be in Tokyo 1 second from now. You cannot be on Mars in the next 5 minutes. And the reason is simple. There is a speed limit. The speed of light. Nothing, no information, no object, no signal of any kind can travel faster than about 300,000 kilometers per second. That is roughly 186,000 miles per second. It is fantastically fast, but it is finite. It is a hard limit, baked into the very structure of space-time. Now, imagine drawing a diagram. Put time going up and one direction of space going sideways. You are sitting at a point in the center. From that point, draw all the paths that light could travel, going forward in time. Since light goes at the maximum possible speed, those light paths form a cone spreading upward from your point. Everything inside that cone, things closer than light could reach in a given time, that is your future. Those are the events you could possibly influence, the places you could possibly reach. Now do the same thing, going backward in time, downward on the diagram. Draw all the light paths coming toward your point from the past. That forms another cone, pointing downward. Everything inside that cone is your past, the events that could have influenced you, the things that could have sent you a signal. Together, those two cones, future cone pointing up, past cone pointing down, form your light cone. And this light cone is one of the most fundamental structures in all of physics. Here is the thing about light cones that matters for our story tonight. In ordinary, flat, uncurved space-time, far from any mass, everyone's light cone points the same way, up, toward the future. The future is always above you on the diagram, and the spatial directions spread out sideways. You can move in any spatial direction, left, right, forward, backward. You have complete freedom in space. But in time, you have no freedom at all. You always move toward the future, always upward on the diagram. You cannot stop time. You cannot go backward. Time is the direction you must move, and space is the direction you can choose. That distinction, time as the direction you must go, and space as the direction you can choose, is one of the deepest features of reality as we know it. It is so fundamental that you do not even think about it. You just live it. But here is where black holes enter the picture. And here is where things get strange. Remember, mass curves space-time. The Earth curves it a little. The Sun curves it more. A white dwarf star curves it quite a bit. A neutron star, one of those insanely dense remnants of a dead star where a teaspoon of material weighs more than 1 billion tons. A neutron star curves space-time a lot. And as you get closer and closer to one of these massive objects, something happens to your light cone. It begins to tilt. Think about that. As space-time curves more and more intensely, the light cone at each point in space begins to tip. Near a moderately massive object, like the Earth, the tipping is incredibly tiny. You would need instruments of extraordinary precision to measure it, but it is there. Near a neutron star, the tipping is more dramatic. The light cones lean noticeably toward the center of the star. What does this tipping mean? It means that the direction of your future, the direction you must go, shifts slightly. Instead of pointing straight up on our diagram, your future tips a little toward the massive object. You can still move away from it, but you have to push harder. Some of your available future has been redirected toward the center. As you get closer and closer to an extremely massive, extremely compact object, the light cones tilt more and more. Your future tips further and further toward the center. Your freedom to move outward, away from the object, diminishes. The range of possible paths narrows. And then you reach the event horizon. At the event horizon, the light cones tilt so far that they are pointing entirely inward. Every single direction you could travel, every possible future, points toward the center. There is no path, no trajectory, no possible motion that leads back out. Not because some force is pulling you, not because you are too weak to escape, but because every direction that exists, every possible future, leads inward. Let me say that again, because it is one of the most extraordinary things in all of physics. At the event horizon of a black hole, all of your possible futures point toward the singularity at the center. Outward is not a direction that exists anymore. The geometry of space-time itself has been curved so extremely that outward is no longer part of your future. It is no longer something you can reach, not even in principle. And this is where the mind-bending part comes in. This is where space and time switch. Let me explain what that actually means. And I want to be careful here, because this is one of those things that is easy to say and hard to really understand. But once it clicks, it is genuinely one of the most astonishing ideas in all of science. Outside the black hole, in our normal everyday universe, you have a clear distinction between space and time. Time is the direction you must move. You cannot stop it, you cannot reverse it. You move inexorably into the future. Space is the direction you can choose. You can move left or right, forward or backward. You have freedom to navigate spatial directions. Now, one of the things that defines time as time, the thing that makes it different from space in the mathematics of relativity, is something called the sign of the metric. I know that sounds technical, but stay with me. In the equations that describe space-time, the time direction and the space directions have different mathematical signs. It is this difference in sign that makes time behave differently from space. Time has one sign, space has the opposite. At the event horizon of a black hole, these signs flip. The radial direction, the direction pointing toward and away from the center of the black hole, changes its mathematical sign. Outside the horizon, the radial direction is spatial. You can move in or out, toward the center or away from it, freely. Inside the horizon, the radial direction becomes time-like. It becomes the direction you must move, and you must move inward, toward the singularity, because inward is now the future, and the time direction, the one that was relentlessly pushing you into the future, the one you could never stop or reverse. It flips to become spatial. Time becomes a direction you can move around in, at least in a sense. Now, I want to be honest about the limits of this description. When physicists say space and time switch places inside a black hole, they are describing something precise that happens in the mathematics of the Schwarzschild metric. In the coordinates Schwarzschild used to describe the geometry, the mathematical character of the radial coordinate and the time coordinate literally exchange roles at the horizon. The variable that was measuring time starts behaving like the variable that was measuring space, and vice versa. It is a precise, well-defined mathematical statement. But what it means for your actual experience, what it would feel like, that is more subtle. You would not suddenly feel time running sideways or space running forward. You would not perceive the swap directly. What you would experience is something arguably even stranger: inevitability. Inside the event horizon, the singularity is not a place in space. It is a moment in time. Sit with that for a second. Outside the black hole, the singularity seems like a location, a point at the center. But once you cross the event horizon, the singularity is not somewhere ahead of you in space. It is somewhere ahead of you in time. It is in your future. And just as you cannot avoid next Tuesday in your normal life, you cannot avoid the singularity inside a black hole. It is not a wall you are heading toward. It is a moment that is coming, inexorably, like the ticking of a clock. You can twist and turn and fire rockets in any direction. You can aim yourself sideways, try to orbit, try to go backward. None of it matters. The singularity is not a place you can steer away from. It is a future you cannot avoid. That is what it means for space and time to switch. The direction that was a choice becomes a destiny. The dimension you could navigate becomes the dimension that carries you, whether you want to go or not. And that, honestly, is one of the most philosophically stunning things physics has ever told us. That the distinction between space and time, which feels so fundamental, so absolute, so obviously true, is actually flexible. It depends on where you are. In extreme conditions, in the warped geometry near a collapsed star, the very categories of space and time can rearrange themselves. But I want to back up a bit, because this idea did not arrive fully formed. It took decades of work, confusion, argument, and brilliant thinking to get to this understanding. And the story of how we figured it out is fascinating in its own right. Let's go back to the early 20th century. Schwarzschild has found his solution. Einstein has presented it. But nobody really knows what to make of the strange behavior at the Schwarzschild radius. Is it a real thing, or just a mathematical artifact? For a long time, most physicists went with the artifact interpretation. The thinking was that the blow-up in the equations at the Schwarzschild radius was just a problem with the coordinate system, like the way the coordinates on a globe go haywire at the North Pole. At the North Pole, lines of longitude all converge to a single point. The coordinates break down, but nothing physically strange happens there. You can stand at the North Pole perfectly comfortably. The coordinate system just cannot handle that specific spot very well. And this intuition was partly right. The singularity in Schwarzschild's equations at the Schwarzschild radius, the event horizon, is in fact a coordinate singularity. It can be removed by choosing better coordinates. The physics at the event horizon is perfectly well behaved. Nothing locally catastrophic happens as you cross it. If you were falling into a sufficiently large black hole, you would cross the event horizon without even noticing. No wall, no barrier, no dramatic flash of light. You would just keep falling. But removing the coordinate singularity did not make the event horizon unimportant. Quite the opposite. It revealed the event horizon for what it truly is: a one-way boundary in space-time, a surface that you can cross inward but never outward. And understanding that took a long time. One of the early breakthroughs came from a physicist named Arthur Eddington, the same Eddington who had confirmed Einstein's general relativity by observing the bending of starlight during the 1919 solar eclipse. In 1924, Eddington proposed a different set of coordinates for the Schwarzschild solution, coordinates that did not blow up at the event horizon. But remarkably, the significance of this was not widely appreciated at the time. Then, in 1933, a brilliant Belgian priest and cosmologist named Georges Lemaitre, the same man who first proposed what we now call the Big Bang theory, showed that the Schwarzschild singularity at the event horizon was indeed a coordinate artifact. He demonstrated that a freely falling observer would pass through the event horizon smoothly without experiencing anything infinite or singular. The physics was perfectly regular, but even Lemaitre's work did not settle the question. Most physicists still believed that real stars could never actually collapse to this point. There would be some force, some mechanism that would prevent the collapse. Nature would not allow an event horizon to form. This belief was reinforced by an influential paper written in 1939 by none other than J. Robert Oppenheimer. Yes, the same Oppenheimer who would later lead the Manhattan Project. Oppenheimer, together with his student Hartland Snyder, published a paper showing that a sufficiently massive star, once it exhausted its nuclear fuel, could indeed collapse all the way down past the Schwarzschild radius. They showed that, from the perspective of a distant observer, the collapse would appear to slow down as the star's surface approached the event horizon. The star would appear to freeze, growing ever dimmer and ever redder, but never quite reaching the horizon. A distant observer would literally never see the star cross its own event horizon. But from the perspective of someone falling with the star's surface, the collapse would proceed just fine. The star would shrink past the Schwarzschild radius and keep going. Nothing special would happen at the crossing. The falling observer and the distant observer would see completely different things. This was deeply confusing. Two observers, looking at the same event, seeing completely different realities. For the distant observer, the star freezes forever at the horizon. For the falling observer, the star zips right through. Both are correct. Neither is lying. They simply occupy different positions in a curved space-time, and space-time looks different from different vantage points. This conflict was so unsettling that Soviet physicists coined the term frozen star for what we now call a black hole. Because from the outside, that is exactly what it looks like. A star frozen in time at the moment of its own collapse, never quite finishing the job. The term black hole, by the way, did not become popular until much later. The American physicist John Wheeler is usually credited with popularizing it around 1967, though the exact origin is debated. Wheeler liked the term because it was vivid and dramatic. The older names, collapsed star, frozen star, gravitationally collapsed object, were accurate but did not capture the imagination the way black hole did. And once Wheeler started using it in lectures and papers, it stuck. But the real conceptual breakthrough, the one that finally made the interior of a black hole comprehensible, came from the work on better coordinate systems. In 1958, a physicist named David Finkelstein published a paper that completely clarified the nature of the event horizon. Building on earlier work by Eddington and others, Finkelstein introduced a coordinate system in which the event horizon was perfectly smooth. No infinities, no singularities, nothing weird at all. His coordinates made the one-way nature of the horizon crystal clear. You could see, right there in the math, that the event horizon was a surface that light and matter could cross in one direction, inward, but never in the other direction. Finkelstein called it a one-way membrane, and that is exactly what it is. Not a wall, not a barrier, not a force field, just a boundary in space-time beyond which all paths lead inward. Then, in 1960, Martin Kruskal and George Sekeres independently found an even more complete coordinate system, one that covered the entire Schwarzschild spacetime, including both the exterior and the interior of the black hole. The Kruskal-Sekeres coordinates, as they came to be known, are still the gold standard for understanding the global structure of a Schwarzschild black hole. And it is in these coordinates that the switching of space and time becomes particularly vivid. In the original Schwarzschild coordinates, outside the event horizon, the time coordinate behaves like time, and the radial coordinate behaves like space. Inside the event horizon, these roles reverse. The radial coordinate becomes time-like, marching inexorably toward the singularity, just as time marches toward the future in ordinary space. And the time coordinate becomes space-like, a direction you can move around in. But let me bring this back to something you can feel. Let's do a thought experiment. Let's fall into a black hole. Now, what happens to you depends enormously on the size of the black hole. And that might be surprising. The reason comes down to tidal forces. Tidal forces are the difference in gravitational pull between two nearby points. You experience tidal forces right now, lying in bed. Your feet, slightly closer to the center of the Earth than your head, feel a slightly stronger gravitational pull. The difference is completely imperceptible. But near a black hole, tidal forces can be enormous. And here is what matters. Tidal forces at the event horizon depend on the mass of the black hole in a way you might not expect. The more massive the black hole, the weaker the tidal forces at the horizon. A more massive black hole has a larger event horizon, and a larger event horizon means the curvature of space-time is gentler, more spread out. So if you fell into a small black hole, say one with the mass of a few suns and a Schwarzschild radius of maybe 10 kilometers, the tidal forces would be ferocious. You would be stretched like taffy, elongated into a thin strand. Physicists call this spaghettification. You would be torn apart long before you reach the horizon. But imagine a supermassive black hole. The black hole at the center of the galaxy, M87, has a mass of about 6.5 billion suns. Its event horizon is larger than our entire solar system. For a black hole that massive, the tidal forces at the event horizon are almost negligible. You could cross the event horizon and feel absolutely nothing unusual. The curvature is so gradual, so smooth at that scale, that locally, right at the horizon, everything feels like normal space. And this is one of the most unsettling things about black holes. The event horizon is not a physical barrier. There is no wall, no membrane, no surface you bounce off of. It is an invisible boundary. You cross it and you do not even know. Nothing locally changes, but something has profoundly changed. Before you crossed the horizon, you had a choice. You could fire your rockets and escape. After you cross the horizon, that choice is gone. Not because your rockets are not powerful enough, but because the geometry of space-time itself has rearranged. Every direction you can possibly travel leads, eventually, to the singularity. Let me paint the picture of what it would be like. You have crossed the event horizon of a supermassive black hole. You felt nothing when you crossed. The stars above you look a little strange, their light bent and distorted. But you are fine. You feel weightless. But now, here is what has changed. Before, the singularity was below you, a point in space at the center. Now, inside the horizon, the singularity is no longer below you. It is ahead of you in time. It is in your future. And just as you cannot avoid next Tuesday, you cannot avoid the singularity. You could fire your rockets in any direction, and either way, you would still reach the singularity. In fact, Firing your rockets to try to escape actually makes you reach the singularity sooner, not later. The best strategy for maximizing your remaining time is to simply freefall, do nothing. Let space-time carry you. Inside the event horizon of M87's black hole, you might have hours before tidal forces become noticeable. Hours of floating in a space where the dimension that used to be space is now behaving like time, and the direction toward the singularity is as inevitable as tomorrow. And during those hours, light from the outside universe can still fall in. Photons that crossed the event horizon after you did can catch up to you. You could look upward and still see stars. But the light would be increasingly distorted, and the view would grow stranger as the curvature intensified. And then, eventually, inevitably, you reach the singularity. In classical general relativity, the singularity is a point of infinite density and infinite curvature. The equations blow up. Physics ceases to function. But most physicists do not believe the singularity is literally a point of infinite density. Infinity, in physics, is usually a sign that your theory has broken down. You have pushed it beyond its domain of validity, and what we are probably missing is quantum mechanics. General relativity ignores quantum effects, and for most situations that is fine. Quantum effects matter at the scale of atoms, not stars. But at the singularity, where all that mass is compressed into an incomprehensibly tiny region, quantum effects cannot be ignored. Gravity is strong, the scale is small. Both quantum mechanics and general relativity are essential, and they do not work together. This is one of the great unsolved problems in physics. We do not have a theory of quantum gravity. String theory tries, loop quantum gravity tries, but none of them is complete, and none has been experimentally verified. So what happens at the singularity remains one of the deepest mysteries in science. Maybe it is smoothed out by quantum effects. Maybe it opens into another region of space-time. Maybe the concepts of space and time break down completely, and something we do not yet have the language for takes their place. We do not know, and that is thrilling. Black holes remind us that there are fundamental questions about reality that remain completely open. But let me take you back out for a moment. Let's talk about how we know these things are real. Because for a long time, black holes were purely theoretical. The story of how black holes went from mathematical curiosities to observed astrophysical objects is one of the great detective stories in science. And it starts with a question that plagued physicists for decades. Can a real star actually collapse to form a black hole? We talked earlier about Oppenheimer and Snyder's 1939 paper showing that massive stars could, in principle, collapse past the Schwarzschild radius. But that paper made a lot of simplifying assumptions. The star was perfectly spherical. It had no pressure, no rotation, no turbulence, no magnetic fields. Real stars are messy. They spin. They pulsate. They have complicated internal dynamics. Many physicists argued that these complications would prevent complete collapse. The star would bounce, or fragment, or shed enough mass to stabilize itself above the event horizon. The resolution came in the 1960s, and it involved one of the most elegant pieces of mathematical physics ever produced. In 1965, a young British mathematician named Roger Penrose published a paper that changed everything. Penrose introduced the concept of a trapped surface, a closed surface, in space-time, where all light rays, even those pointing outward, are actually moving inward. He showed that once a trapped surface forms, which happens when enough mass is concentrated in a small enough region, the collapse to a singularity is inevitable. It does not matter if the star is lumpy, rotating, asymmetric, or turbulent. Once the matter crosses a certain threshold of compaction, the geometry of space-time itself guarantees the formation of a singularity. This is Penrose's singularity theorem, and it is a work of mathematical brilliance. It does not assume any special symmetry. It applies to the messy, complicated, real universe, and it tells us that singularities, and by extension, event horizons and black holes, are not just mathematical possibilities. They are predictions. They are what general relativity says must happen when massive stars die. Penrose shared the 2020 Nobel Prize in Physics for this work, 55 years after the original paper. Sometimes the universe takes its time in recognizing genius. Now, Penrose's theorem tells us that black holes must form. But do they actually exist out there in the universe? That is an observational question, and answering it required decades of increasingly clever detective work. The first strong candidate was discovered in 1964, purely by accident. Riccardo Giacconi and his team were conducting one of the first X-ray surveys of the sky, using a small rocket-launched detector. They found a powerful X-ray source in the constellation Cygnus, which they named Cygnus X1. It was one of the brightest X-ray sources in the sky, and it was paired with a visible companion star, a blue supergiant called HDE 226868. Over the next several years, detailed observations revealed something remarkable. The companion star was orbiting an invisible partner. By tracking the star's orbital motion, astronomers could estimate the mass of the unseen object. It came out to roughly 15 times the mass of the Sun, and that was too heavy. Way too heavy. See, there are only a few things a compact, invisible astrophysical object can be. It could be a white dwarf, the dense remnant of a star like our Sun, but white dwarfs cannot be heavier than about 1.4 solar masses. Beyond that, electron degeneracy pressure cannot support them, and they collapse. That mass limit was calculated by a young Indian physicist named Subrahmanyan Chandrasekhar in 1930, during a steamship voyage from India to England. He was 19 years old. Chandrasekhar's limit, as it came to be known, earned him the Nobel Prize in 1983, more than half a century after his discovery. Another case of the universe being slow to give credit. If the invisible object in Cygnus X1 was too heavy to be a white dwarf, could it be a neutron star? Neutron stars are even denser, compressed so tightly that protons and electrons are crushed together into neutrons. A teaspoon of neutron star material weighs about 1 billion tons. But even neutron stars have a mass limit, typically estimated at around 2 to 3 solar masses, beyond which neutron degeneracy pressure cannot hold them up. 15 solar masses blows past both limits. The invisible object in Cygnus X1 was too massive to be a white dwarf, too massive to be a neutron star. The only remaining option, according to our understanding of physics, was a black hole. And the X-rays made perfect sense. Material from the companion star, pulled off by the black hole's gravity, would spiral inward, forming a disk of superheated gas around the black hole, an accretion disk. As the gas spirals in, it compresses, heats up, and reaches temperatures of millions of degrees. At those temperatures, it radiates intensely in X-rays. The X-rays Giacconi's team detected were the dying screams of matter being swallowed by a black hole. There is a famous bet about Cygnus X1 that tells you something about how controversial this was at the time. In 1974, Stephen Hawking bet his colleague Kip Thorne that Cygnus X1 was not a black hole. Now, Hawking had spent much of his career studying black holes. He was one of the world's foremost experts on them. So why would he bet against their existence? Hawking himself explained it as an insurance policy. He had invested so much of his intellectual life in black holes that if they turned out not to exist, at least he would win the bet and get the consolation prize, which was a subscription to the satirical magazine Private Eye. If black holes did exist, well, he would lose the bet, but his life's work would be validated. a fair trade. In 1990, with the evidence for Cygnus X1 being a black hole now overwhelming, Hawking conceded the bet. He reportedly broke into Thorne's office in the middle of the night to sign the bet concession, thumbprint and all. But Cygnus X1 was just the beginning. Over the following decades, astronomers found more and more black hole candidates, stellar mass black holes in binary systems, revealed by their X-ray emissions, supermassive black holes at the centers of galaxies, revealed by the orbital motions of stars, whipping around an invisible center of enormous mass. In our own Milky Way, a team led by Reinhard Genzel and Andrea Ghez spent years painstakingly tracking the orbits of stars near the galactic center, using infrared telescopes that could peer through the dust obscuring the heart of the galaxy. They found stars orbiting at tremendous speeds around a completely invisible point. One star, called S2, completes its orbit in about 16 years and reaches speeds of nearly 8,000 kilometers per second, almost 3% of the speed of light, as it whips around the central object. From these orbits, the mass of the central object could be precisely determined, about 4 million solar masses, compressed into a region smaller than our solar system. Nothing we know of, besides a black hole, can pack that much mass into that little space. Genzel and Ghez shared the Nobel Prize in Physics in 2020, alongside Roger Penrose, for this observational work. And then, in 2019, came the image. The Event Horizon Telescope, or EHT, is not a single telescope. It is a planet-sized array of radio telescopes spread across the globe, from Hawaii to Spain to the South Pole, all working together as a single instrument through a technique called Very Long Baseline Interferometry. By combining data from all these far-flung dishes, the EHT achieves an effective angular resolution, equivalent to being able to read a newspaper in New York from a cafe in Paris. In April 2019, the EHT collaboration released the first direct image of a black hole's shadow, the black hole at the center of the galaxy M87. That glowing orange ring, asymmetric and beautiful, encircling a dark void. That image was not the black hole itself. It was the superheated gas swirling around the black hole, the accretion disk, with the dark center being the shadow of the event horizon, the region where light falls in and never comes back out. It was arguably the most profound photograph ever taken, a direct image of a boundary in space-time, a one-way door in the fabric of reality. 2 years later, in 2022, the EHT released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Our black hole, the one sitting at the center of the spiral of stars you can see on a clear, dark night, that faint band of light stretching across the sky. Right now, tonight, as you lie in bed, there is a black hole with the mass of 4 million suns at the center of the galaxy. It is about 26,000 light-years away. The light that left its vicinity 26,000 years ago, when our ancestors were painting on cave walls, is only now reaching your neighborhood. And inside that black hole, right now, space and time are switched. The singularity is not a place, it is a future. And matter that crosses the event horizon falls not through space, but through time, toward an endpoint that nobody fully understands. That is happening right now, in the middle of our galaxy. But let me tell you about another piece of this story, one that involves the most famous physicist of the late 20th century, and an argument that is still raging today. Let me tell you about Stephen Hawking and the information paradox. In 1974, Hawking made a discovery that shocked the physics community. He showed that black holes are not completely black. They glow. This sounds impossible. The entire defining feature of a black hole is that nothing can escape from inside the event horizon. So how can a black hole emit anything? The answer lies in quantum mechanics. Remember, we said earlier that quantum mechanics and general relativity do not work well together. We do not have a full theory of quantum gravity. But Hawking did something clever. Instead of trying to solve the full quantum gravity problem, he studied quantum fields, the fundamental ingredients of the universe, photons, electrons, the quantum stuff that makes up everything, in the curved space-time around a black hole. He used general relativity to describe the space-time and quantum mechanics to describe the fields living in that space-time, a hybrid approach, sometimes called semi-classical gravity. And what he found was astonishing. The quantum vacuum, what we usually think of as empty space, is not really empty. It seethes with fluctuations. Pairs of virtual particles constantly pop into existence and then annihilate each other, appearing and disappearing in a frantic quantum dance. In flat space-time, far from any mass, this has no measurable consequences. The particles appear and vanish so quickly that you never notice them. But near the event horizon of a black hole, something different can happen. A pair of virtual particles can pop into existence right at the edge of the horizon. One of the pair falls in, the other escapes outward, becoming a real particle that flies away into space. From a distance, it looks like the black hole just emitted a particle. Now, this is a simplified picture. Hawking's actual calculation is much more mathematically rigorous and does not literally involve virtual particles splitting at the horizon. That is a popular visualization that captures some of the flavor, but not the precision. What Hawking actually showed is that the quantum vacuum state that a freely falling observer would consider empty is not the same vacuum state that a distant observer considers empty. The disagreement between these two perspectives, which is a real physical effect caused by the curvature of space-time, means that a distant observer sees thermal radiation emanating from the black hole. This radiation is called Hawking radiation, and it has a temperature. The temperature depends on the mass of the black hole, and it has a beautiful and simple formula. The temperature is inversely proportional to the mass. Bigger black holes are colder. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. That is unimaginably cold, far colder than the cosmic microwave background, which is about 2.7 Kelvin. So solar mass black holes emit far less radiation than they absorb from their environment. They are growing, not shrinking. But in principle, if you isolated a black hole completely and waited long enough, an unimaginably long time, far longer than the current age of the universe, the black hole would slowly evaporate. It would radiate away its mass, getting smaller and hotter, radiating faster and faster, until in a final burst of energy, it would vanish completely. That is mind-blowing enough on its own. Black holes are not eternal. They die, slowly, almost incomprehensibly slowly, but they die. But the real problem, the one that has kept theoretical physicists up at night for 50 years, is not the evaporation itself. It is what happens to the information. Here is the problem. In quantum mechanics, there is a fundamental principle that information is never destroyed. This is not a casual statement about data storage. It is a deep mathematical property of quantum theory. The equations of quantum mechanics are unitary, which is a technical way of saying that they are reversible. In principle, if you knew the complete quantum state of a system at any moment, you could work backward and figure out what it was at any earlier moment. Information is conserved. Nothing is lost. Now, think about what happens when something falls into a black hole, and the black hole eventually evaporates. A book falls in. The book contains information, the arrangement of its atoms, the text on its pages, the quantum state of every particle in it. The book crosses the event horizon and is gone. The black hole eventually evaporates through Hawking radiation, but Hawking's original calculation showed that the radiation is thermal, random. It carries no information about what fell in. It is like the heat coming off a radiator. It tells you the temperature, but nothing about the fuel. So where did the information in the book go? It did not come out in the Hawking radiation, because the radiation is random. It cannot be inside the black hole, because the black hole has evaporated. It is just gone. But that violates quantum mechanics. Information cannot be destroyed. This is the black hole information paradox, and it is one of the deepest problems in theoretical physics. It sits right at the intersection of quantum mechanics and general relativity, the two pillars of modern physics, and it tells us that at least one of them must be incomplete. For years, Hawking himself argued that information was genuinely lost. He said that black holes destroyed information and that quantum mechanics needed to be modified to account for this. This was a radical position, and most other physicists disagreed. They believed that information must somehow escape, perhaps encoded in subtle correlations in the Hawking radiation that Hawking's original calculation did not capture. In 2004, Hawking conceded. He announced that he now believed information was preserved, that it does somehow get out in the Hawking radiation. He paid off a bet with the Caltech physicist John Preskill, giving him a baseball encyclopedia, a tongue-in-cheek acknowledgement that information had been recovered. But here is the thing. Hawking conceded that information is preserved, but he did not fully explain how. And that question, how does information escape a black hole, is still not completely answered. There are promising ideas. There is beautiful work involving something called the Page curve, which describes how the entanglement entropy of the Hawking radiation should behave over time if information is preserved. In 2019 and 2020, several groups of physicists made remarkable progress on deriving the Page curve using a surprising mathematical tool called the island formula, which suggests that the interior of the black hole, the part behind the event horizon, eventually becomes encoded in the radiation outside. This is cutting-edge stuff. It is happening right now as you lie here. Somewhere tonight, some physicist is probably staring at equations, trying to figure out exactly how the interior of a black hole, a region where space and time have swapped, manages to teleport its secrets to the outside universe. And the information paradox connects directly to our central theme, because the paradox is fundamentally about what the event horizon means. Is it a true boundary, a genuine one-way door that severs the inside from the outside, or is it something more subtle, a boundary that appears absolute from a classical perspective, but becomes permeable when quantum effects are included? Some physicists have proposed even more radical ideas. In 2012, a group of physicists known as AMPS, after the author's initials, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, proposed what became known as the firewall paradox. They argued that if information is preserved in the Hawking radiation, and if certain other principles of quantum mechanics hold, then the event horizon cannot be the smooth, uneventful boundary that general relativity predicts. Instead, it would be a wall of high-energy radiation, a firewall, that would incinerate anything crossing it. This is a shocking conclusion. General relativity says the horizon is smooth. The firewall argument says it is lethal, and both arguments seem rigorous within their own frameworks. They cannot both be right. Something has to give. The firewall paradox is still unresolved. It remains one of the most active areas of debate in theoretical physics. And it tells us something important. The event horizon, that boundary where space and time switch, is not just a curiosity. It is a crucible where our deepest theories are tested and found wanting. The answers to the questions that the event horizon poses may require entirely new physics, a new understanding of space-time, information, and reality itself. But let me steer us back from the cutting edge and towards something a little more grounding, because we have been deep inside theoretical physics for a while, and I think it is worth pausing to appreciate something remarkable. We figured this out, humans, these fragile, short-lived creatures on a small, rocky planet, orbiting an unremarkable star in the outer arm of a spiral galaxy. We figured out what happens inside a black hole. We cannot go there. We cannot send a probe. We cannot perform a direct experiment. And yet, through the power of mathematics, logic, and careful reasoning, we have deduced that inside a region where space-time is warped beyond recognition, the very roles of space and time reverse. We know this not because we have seen it, but because our equations, tested and verified in countless other contexts, tell us it must be so. That is extraordinary. That is one of the most impressive things our species has ever done, and we did it through a chain of genius and persistence spanning centuries. From Newton's laws to Einstein's space-time, from Schwarzschild's solution in the trenches to Penrose's singularity theorems, from Hawking's radiation to the Event Horizon Telescope's photograph, each generation building on the one before, correcting mistakes, resolving paradoxes, and pushing the boundary of understanding a little further into the dark. Now, I want to come back to the central idea one more time, because I think there are layers to it that we have not fully explored, and the more you sit with it, the more profound it becomes. Space and time switch places inside a black hole. We have talked about what this means mathematically, the sign flip in the metric, the tipping of light cones, the radial direction becoming time-like. We have talked about what it means experientially, the singularity becoming a future moment rather than a location, the impossibility of avoiding it, the uselessness of rockets. But there is a deeper philosophical dimension here that I think is worth lingering on. In our everyday experience, space and time feel fundamentally different. Space is democratic. You can go left or right, up or down, forward or back. You have choices. You have agency. Time, on the other hand, is authoritarian. It moves in one direction. It does not ask your permission. You cannot go back. You cannot stop. You can only go forward. This asymmetry between space and time is so deep, so baked into our experience, that it feels like a fundamental law of reality. Space gives you freedom. Time gives you necessity. But black holes tell us that this asymmetry is not fundamental at all. It is contingent. It depends on the geometry of the space-time you happen to be in. In the mildly curved space-time of your bedroom, space is spatial and time is temporal, just as you expect. But in the violently curved space-time inside a black hole, the roles reverse. What was freedom becomes necessity. What was necessity becomes freedom, or at least something with the mathematical character of freedom. This suggests something remarkable about the nature of reality, the distinction between space and time, which feels so absolute, so unquestionable, is actually a feature of the local geometry. It is like the difference between uphill and downhill. On flat ground, there is no uphill or downhill. The distinction only emerges when the ground curves. Similarly, the distinction between which direction is space and which is time only takes on its familiar form in a particular geometric context. Change the geometry drastically enough, and the distinction itself changes, and that is wild. because it means that space and time are not the permanent, fixed stage on which physics plays out. They are more like roles in a drama, roles that can be assigned and reassigned depending on the shape of the stage itself. The stage is space-time, and the roles that different directions play within it depend on how space-time is curved. Some physicists think this hints at something even deeper. If space and time are not fundamental, if they can switch and morph depending on the geometry, then maybe they are emergent. Maybe they arise from something more basic, something that does not have the character of either space or time. Several approaches to quantum gravity, including some ideas in string theory and the program known as it from qubit, suggest that space-time itself might emerge from quantum entanglement, from the correlations between quantum systems. If that is true, then space and time, the concepts that have defined human experience since the first conscious being opened its eyes, are not the bedrock of reality. They are the surface, the appearance, and the real nature of reality lies somewhere beneath, in a structure that we do not yet have the words for. But I want to bring this back to Earth, literally, because here is something wonderful. You do not need to fall into a black hole to experience the flexibility of space and time. You experience it every day, right now. Remember, gravity curves space-time. The Earth curves space-time. And one of the consequences of curved space-time is that time flows at different rates at different places. Time runs slightly slower, close to a massive object, and slightly faster, farther away. This is not science fiction. This is measured fact. The clocks on GPS satellites, orbiting about 20,200 kilometers above the Earth, tick faster than clocks on the ground by about 38 microseconds per day. That sounds tiny, but if the GPS system did not correct for this, your position fix would drift by about 10 kilometers per day. Your phone's navigation works precisely because Einstein's general relativity is programmed into the satellites. And it goes further. A clock on the floor of your room ticks very slightly slower than a clock on your shelf, because the floor is closer to the center of the Earth and deeper in the gravitational well. The difference is absurdly small, billionths of a second, but it has been directly measured with atomic clocks. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, measured the difference in the rate of time between two atomic clocks, separated by just 33 centimeters, about a foot. The lower clock ticked slower. Time literally runs slower for your feet than for your head. Right now, as you lie there, the time at your feet and the time at your head are moving at slightly different rates. This is the same physics that switches space and time inside a black hole. It is the same equations, the same geometry, just at a much, much milder intensity. Near the Earth, space-time is barely curved, and the effects are tiny. Near a black hole, space-time is so drastically curved that the effects become total, absolute, reality redefining. But it is all the same phenomenon, a continuous spectrum from the gentle curvature you are swimming in right now to the extreme curvature inside a black hole where space and time fully exchange their natures. You are living in the gentle version of the same physics that creates event horizons and singularities and regions where the future is not a time, but a place. Let me take you on one more journey before we start to wind down, because there is one more piece of this story that I think is beautiful and important, and it connects black holes to the largest scales in the universe. Black holes are not just bizarre endpoints of stellar evolution. They are architects. They shape the galaxies they live in, and through that, they shape the entire cosmos. We mentioned earlier that most large galaxies, possibly all of them, harbor supermassive black holes at their centers. The Milky Way has Sagittarius A star with its 4 million solar masses. But that is actually on the small side. The supermassive black holes in some galaxies are monsters, billions of solar masses heavy. The black hole in the galaxy NGC 4889, for instance, is estimated at about 21 billion solar masses. Try to even conceive of that. 21 billion times the mass of the Sun, compressed inside an event horizon that is many times larger than our solar system. And these supermassive black holes are not passive tenants, quietly sitting at the center of their galaxies. They are dynamic, influential, and sometimes violent. When a supermassive black hole is actively consuming material, drawing in gas and dust from its surroundings, it forms a swirling disk of superheated matter, an accretion disk, that can outshine the entire rest of the galaxy. When this happens, we call it an active galactic nucleus, or AGN. In the most extreme cases, the black hole launches enormous jets of material outward at nearly the speed of light. Jets that can extend for hundreds of thousands of light years, far beyond the boundaries of the host galaxy. These jets carry enormous amounts of energy. They heat the gas in the galaxy, prevent it from cooling and collapsing to form new stars, and regulate the growth of the galaxy as a whole. Without the supermassive black hole at the center, galaxies would grow differently. Stars would form at different rates. The entire structure of the visible universe would be altered. There is a remarkable relationship between the mass of a galaxy's central black hole and the mass of its central bulge, the spheroidal concentration of stars at the heart of the galaxy. This relationship, called the M-sigma relation, holds across an enormous range of galaxy sizes. The black hole is always a tiny fraction of the galaxy's mass, typically about 0.1%, but the correlation is tight and precise. This suggests that the black hole and its host galaxy co-evolve. They grow together, influencing each other through a complex feedback loop of gravity, radiation, jets, and star formation. The black hole shapes the galaxy, and the galaxy feeds the black hole. It is a symbiotic relationship playing out over billions of years, spanning scales from the event horizon, a region of space-time where space and time have swapped, to the entire galaxy, a structure spanning 100,000 light-years. And the connection goes even further. Some cosmologists think that supermassive black holes played a crucial role in the early universe, during the first few 100 million years after the Big Bang. The early universe was filled with gas, mostly hydrogen and helium, and this gas needed to collapse and condense to form the first stars and galaxies. Supermassive black holes, or their progenitors, may have acted as seeds around which the first galaxies formed, their gravity drawing in the surrounding gas and kickstarting the process of galaxy formation. How these supermassive black holes formed in the first place is itself a major unsolved problem. We have detected quasars, extremely luminous active galactic nuclei powered by supermassive black holes from the very early universe. Some of these quasars are seen as they were when the universe was less than 1 billion years old, and they contain black holes of billions of solar masses. How did such enormous black holes grow so big so fast? The universe simply was not old enough for them to have formed from stellar mass black holes, merging and accreting gas at normal rates. There must have been a faster mechanism, maybe direct collapse of enormous gas clouds, maybe mergers of smaller black holes that were themselves unusually large, maybe exotic processes in the very early universe that we have not yet understood. This is an active area of research, and every year brings new data from telescopes like the James Webb Space Telescope, which is peering deeper into the early universe than anything before it. But let me take this in another direction. Because black holes connect to cosmology in a way that is even more surprising and thought-provoking. You know that the universe is expanding. Everywhere you look, galaxies are moving apart from each other. Space itself is stretching. This was discovered by Edwin Hubble in 1929, and it is one of the most well-established facts in all of science. Now, this expansion has a fascinating consequence for the very concept of an event horizon, because the universe does not just have black hole event horizons, it has a cosmological event horizon, because the universe is expanding, and the expansion is accelerating, driven by what we call dark energy. There are galaxies so far away from us that they are receding faster than the speed of light, not faster than light through space, but faster than light due to the expansion of space itself. Light from those galaxies will never reach us. They are beyond our cosmic horizon, our cosmological event horizon. And here is the deep connection. The cosmological event horizon is, in a fundamental sense, the mirror image of a black hole event horizon. A black hole event horizon is a boundary that you can cross inward but never outward. A cosmological event horizon is a boundary beyond which things can never reach you. In a black hole, you are trapped inside. In the expanding universe, distant galaxies are trapped outside. Both are one-way boundaries in space-time, and both arise from the geometry of the universe itself. Some physicists, most notably the Dutch Nobel laureate Gerard Hooft and the American physicist Leonard Susskind, have pushed this analogy further with the holographic principle. This is the idea that all the information about a region of space can be encoded on the boundary of that region, like a hologram. The amount of information that can be contained within a region of space is not proportional to the volume of the region, as you might naively expect, but to the area of its boundary, specifically, the area of its event horizon. For black holes, this was first noticed by Jacob Bekenstein in the early 1970s and refined by Hawking. Bekenstein showed that the entropy of a black hole, a measure of how much information it contains, is proportional to the area of the event horizon, not the volume of the interior. This was deeply strange. In every other system in physics, entropy scales with volume. You double the volume, you roughly double the entropy. But for black holes, entropy scales with area. The information is on the surface, not in the bulk. This has led some physicists to propose that our entire universe might be a hologram, that the three-dimensional reality we experience might be a projection of information encoded on a distant two-dimensional surface, perhaps the cosmological event horizon. This is the holographic principle, and it remains one of the most provocative ideas in modern theoretical physics. Is it true? We do not know. It is a theoretical proposal, not an experimentally verified fact. But it emerges naturally from the physics of black holes, from the switching of space and time at the event horizon, and from the deep connections between gravity, quantum mechanics, and information. And it all comes back to this central mystery. Inside a black hole, space and time switch. The event horizon is a boundary where the fabric of reality rearranges itself. And that rearrangement has consequences that reach all the way from the quantum vacuum to the large-scale structure of the cosmos. Let me tell you one more story before we begin to settle in. It is about spinning black holes, and it adds another layer of strangeness to an already strange picture. Everything we have discussed so far has been about the simplest possible black hole, the Schwarzschild black hole, which is perfectly spherical and not spinning. But in reality, every black hole we have ever observed is spinning, and often they are spinning very fast. This makes sense when you think about it. Stars spin. The gas clouds from which stars form spin. Angular momentum is conserved. When a massive star collapses to form a black hole, All that spin gets concentrated into a much smaller space. Just like an ice skater, pulling in their arms speeds up their rotation. Black holes spin, and some of them spin at a significant fraction of the speed of light. The geometry of a spinning black hole is described by the Kerr metric, found by the New Zealand mathematician Roy Kerr in 1963. And the Kerr metric is far more complex and far more interesting than the Schwarzschild solution. A spinning black hole has not one but two event horizons, an outer one and an inner one. Between these two horizons, the switching of space and time still occurs. But the geometry is richer, more nuanced, and outside the outer event horizon, there is a region called the ergosphere. The ergosphere is remarkable. Inside the ergosphere, space-time is being dragged around by the spin of the black hole. This effect, called frame dragging, was predicted by general relativity and has been directly measured around the Earth, though the effect near Earth is extremely tiny. Near a spinning black hole, frame dragging is intense. Inside the ergosphere, space-time is dragged so violently that you cannot stand still. No matter how powerful your rockets, no matter how hard you try, you are forced to co-rotate with the black hole. You must spin, but you can still escape from the ergosphere. The outer event horizon is still the point of no return, and the ergosphere extends beyond it. You are being dragged around, forced to spin, but you can still fly away. And here is where it gets really interesting. In 1969, Roger Penrose, the same Penrose who proved the singularity theorems, proposed a thought experiment for extracting energy from a spinning black hole. The idea is this: you send an object into the ergosphere. Inside the ergosphere, you split it in two. One piece falls into the black hole. The other piece is flung back out. If you do this cleverly, the piece that comes out can carry more energy than the original object went in with. The extra energy comes from the rotational energy of the black hole. You have slowed the black hole's spin and extracted that energy. This is the Penrose process, and it is a legitimate, physically valid way to extract energy from a black hole. The black hole spins a little slower. You get the energy. It is like a cosmic power plant, tapping into the rotation of a singularity, hidden behind an event horizon where space and time have switched places. There are even more exotic versions of this. The physicist Roger Blandford and Roman Znayak showed that magnetic fields threading through a spinning black hole's ergosphere can extract rotational energy and channel it into the enormous jets we observe emanating from active galactic nuclei. The most powerful sustained energy sources in the observable universe, quasar jets that outshine entire galaxies, may be powered by the Penrose process, operating through magnetic fields around a spinning black hole. Energy extracted from the place where space and time have switched, powering the brightest objects in the cosmos. If that is not poetry written in the language of physics, I do not know what is. Now, the inner horizon of a Kerr black hole adds yet another layer of intrigue. Between the outer and inner horizons, the radial direction is time-like, just as in the Schwarzschild case. You must move inward, toward the inner horizon. Space and time have switched, just as before. But at the inner horizon, they switch back. The radial direction becomes spatial again. And inside the inner horizon, the equations predict something even stranger. The possibility of a ring-shaped singularity. Not a point, but a ring. And the theoretical possibility of traveling through the ring too. Somewhere else. Where? That depends on which theoretical physicist you ask. Some solutions suggest you could emerge into another universe. Others suggest a white hole, the time reverse of a black hole, a region from which everything is expelled and nothing can enter. The Penrose diagram, a particular way of mapping the global structure of the space-time, shows an infinite chain of alternating universes connected by the Kerr black hole's interior. But I want to be honest with you here. Most physicists are deeply skeptical that any of this would actually happen in a real spinning black hole. The inner horizon of a Kerr black hole is thought to be unstable. Any tiny perturbation, any matter or radiation falling in, would pile up at the inner horizon due to an infinite blue shift effect, potentially creating a singularity at the inner horizon itself and blocking any passage through the ring. This was shown in a series of calculations starting in the late 1960s, and the general consensus is that the beautiful, infinite universe picture of the Kerr interior is a mathematical artifact of the perfect, idealized solution and would not survive in the real, messy universe. But even so, the fact that Einstein's equations can produce such structures, can describe geometries where space and time switch and switch back, where ring-shaped singularities act as portals, where the interior of a spinning black hole contains corridors to other realms, is remarkable. The mathematics of general relativity has a richness and a wildness to it that far exceeds what we observe. The universe is stranger than we can directly experience, and the equations know it, even when we are not sure which parts of the mathematics correspond to reality. Let me take you somewhere else now, somewhere that connects the micro and the macro in a way that is particularly beautiful. Let me tell you about what black holes have taught us about thermodynamics. Thermodynamics. That might sound like a dry subject, the physics of heat engines and steam. But thermodynamics is actually one of the deepest and most universal frameworks in all of science. Its laws apply everywhere, from the inside of your refrigerator, to the cores of stars, to the heat death of the universe. And it turns out that black holes obey thermodynamic laws in a way that is both surprising and profoundly meaningful. This story begins in 1972 with a graduate student at Princeton named Jacob Bekenstein. Bekenstein was thinking about a simple but provocative question. If you throw a cup of hot tea into a black hole, the tea has entropy. Entropy, very roughly, is a measure of disorder, or more precisely, a measure of how many different microscopic arrangements could produce the same macroscopic state. A cup of hot tea has a lot of entropy, all those water molecules jiggling around in trillions of possible configurations. If the tea falls into the black hole, and the black hole is just a featureless gravitational pit, then the entropy of the tea is simply gone. It has vanished from the universe. But the second law of thermodynamics says that entropy can never decrease. The total entropy of the universe must always go up, or at least stay the same. So either the second law of thermodynamics breaks down when black holes are involved, which would be a very big deal, or the black hole itself must have entropy. It must somehow absorb the entropy of the tea and keep the cosmic books balanced. Bekenstein proposed that black holes do have entropy, and that it is proportional to the area of the event horizon. Every time something falls into a black hole, the event horizon grows, and the entropy of the black hole increases. The second law is preserved. The entropy of the universe keeps going up, just as thermodynamics demands. This was a bold proposal, and not everyone was convinced. Hawking himself initially disagreed. If a black hole has entropy, it must also have a temperature, and if it has a temperature, it must radiate. But nothing escapes a black hole. So a black hole cannot have a temperature, so it cannot have entropy. So Bekenstein must be wrong. But then Hawking did his calculation, and he found that black holes do radiate. They have a temperature. Bekenstein was right all along. The result was breathtaking. Black holes are not just gravitational objects. They are thermodynamic objects. They have temperature, entropy, and they obey thermodynamic laws. Specifically, there are 4 laws of black hole mechanics that exactly mirror the 4 laws of thermodynamics. The 0th law of thermodynamics says that temperature is uniform throughout a system in equilibrium. The 0th law of black hole mechanics says that the surface gravity of a stationary black hole is uniform across the event horizon. Surface gravity plays the role of temperature. The first law of thermodynamics is conservation of energy. The first law of black hole mechanics relates changes in the mass, spin, and charge of a black hole to changes in its horizon area. Energy is conserved. The second law of thermodynamics says entropy never decreases. The second law of black hole mechanics, proved by Hawking in 1971, says the area of the event horizon never decreases in any classical process. Area plays the role of entropy. This is Hawking's area theorem, and it is one of his most famous results. It says that if 2 black holes merge, the area of the resulting black hole is at least as large as the sum of the original areas. Event horizons can grow, but they cannot shrink, at least classically. When you include Hawking radiation, which is a quantum effect, the event horizon can shrink as the black hole evaporates. This is analogous to how entropy can decrease locally in thermodynamics if you allow quantum fluctuations. The generalized second law, proposed by Bekenstein, says that the total entropy, ordinary entropy plus black hole entropy, never decreases. The books always balance. And the third law of thermodynamics says you can never reach absolute zero. The third law of black hole mechanics says you can never reduce the surface gravity of a black hole to zero, at least not in a finite number of steps. This corresponds to an extremal black hole, one that is spinning as fast as it possibly can, or carrying as much electric charge as it can hold. The parallels are exact, and they are not a coincidence. They are telling us something profound about the nature of reality. What they are telling us, many physicists believe, is that space-time itself has a microscopic structure. Just as the entropy of a gas comes from the microscopic arrangement of its molecules, the entropy of a black hole must come from the microscopic structure of space-time at the event horizon. There must be tiny, discrete, quantum degrees of freedom associated with the event horizon, quantum bits of space-time that account for the black hole's entropy. And this is where things get really deep. Because the entropy of a black hole, the Bekenstein-Hawking entropy, is enormous. It is given by the area of the event horizon divided by 4 times the Planck area. The Planck area is the square of the Planck length, which is about 1.6 times 10 to the negative 35 meters, an almost inconceivably tiny distance. For a black hole, with the mass of the Sun, the entropy works out to about 10 to the 77. That is a 1 followed by 77 zeros. For comparison, the total entropy of everything else in the observable universe is estimated at about 10 to the 90, and most of that is in the supermassive black holes at the centers of galaxies. Black holes are, by far, the highest entropy objects in the universe. They represent the maximum possible entropy that can be contained within a given region of space. And the fact that this maximum entropy scales with area rather than volume is one of the biggest clues we have about the nature of quantum gravity. If entropy counts the number of microscopic states, and if the entropy of a black hole is proportional to the area of its event horizon, then the number of quantum states, the fundamental bits of information that describe the interior of the black hole, must be encoded on the surface, not in the volume. This is the essence of the holographic principle we touched on earlier, and it brings us full circle, in a way. Space and time switch inside a black hole. The interior is hidden behind an event horizon, and yet all the information about what is inside, all the quantum states, all the microscopic structure, may be stored on the two-dimensional surface of the horizon itself. The interior, this bizarre region where radial space has become time and the singularity is a future you cannot avoid, may be entirely reconstructible from data on the boundary. That is the holographic principle, and it suggests that the three-dimensional interior, the region where space and time are flipped, might not be the fundamental description at all. It might be a projection, an emergent phenomenon, encoded in a more fundamental two-dimensional description on the horizon. If that is true, then what we think of as the inside of a black hole, with all its strangeness and all its switching of space and time, is not the deepest level of reality. It is an interpretation, a way of experiencing something that can be equally well described without any interior at all, just using data on a surface. Now, I want to be careful here. This is speculative. The holographic principle is well established in certain theoretical contexts, particularly in a framework called the AD-CFT correspondence, discovered by the Argentine-American physicist Juan Maldacena in 1997. Maldacena's discovery showed that a theory of gravity in a particular kind of curved spacetime, anti-de Sitter space, is exactly equivalent to a quantum theory without gravity living on the boundary of that spacetime. It is a precise mathematical duality, two completely different-looking theories, one with gravity and extra dimensions, one without, that describe exactly the same physics. This was one of the most important theoretical discoveries of the late 20th century, and it provides strong evidence for the holographic principle. But our universe is not anti-de Sitter space. Our universe has a positive cosmological constant, driven by dark energy, and extending Maldacena's results to our actual universe remains an open problem. So we do not know, for certain, that our universe is a hologram. We do not know, for certain, that the interior of a real black hole is fully encoded on its event horizon. But the evidence points in that direction, and the breadth and depth of theoretical support for these ideas is impressive. And it all started with a student throwing a cup of tea into a black hole and asking a simple question about entropy. Let me tell you about one more thing, something that happened not in a theoretical calculation, but in a laboratory. Well, not a laboratory exactly, an observatory. Actually, multiple observatories. On September 14, 2015, at 5:51 in the morning Eastern Time, both detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, one in Hanford, Washington, and one in Livingston, Louisiana, simultaneously registered a tiny signal, a faint chirp, a ripple in the fabric of spacetime itself. The signal lasted less than 0.2 of a second, but when the data was analyzed, it told an extraordinary story. Two black holes, one about 36 solar masses and one about 29 solar masses, had been spiraling around each other, orbiting faster and faster, getting closer and closer, until they merged into a single black hole of about 62 solar masses. Wait, 36 plus 29 is 65, not 62. Where did the missing 3 solar masses go? They were radiated away as gravitational waves, pure ripples in spacetime. 3 solar masses worth of energy, converted into vibrations of the fabric of the universe, and sent outward at the speed of light in all directions. In those final, frantic moments before the merger, the two black holes were converting mass into gravitational wave energy at a rate greater than the combined light output of every star in the observable universe. For a brief instant, this pair of merging black holes was the brightest thing in the cosmos, not in light, but in gravitational waves. And those waves, after traveling for about 1.3 billion years across the universe, reached Earth and stretched and compressed the 4-kilometer arms of the LIGO detectors, by a distance of about 1,000th the diameter of a proton. 1,000th the diameter of a proton. That is how sensitive LIGO is. It is one of the most precise measurement instruments ever built by humans. The detection of gravitational waves from merging black holes was the final, definitive confirmation of general relativity's predictions about black holes. We had heard them. We had detected the vibrations of space-time caused by event horizons colliding, two regions where space and time are switched, crashing together, merging their geometries, and sending a shockwave of warped space-time across the universe. Since that first detection, LIGO and its European counterpart Virgo have detected dozens more mergers. Black hole pairs, neutron star pairs, even a black hole swallowing a neutron star. Each detection tells us more about the properties of black holes, their masses, their spins, their populations. And each detection is a direct observation of space-time doing something extraordinary, curving, vibrating, radiating, exactly as Einstein's equations predicted more than a century ago. The physicists who made LIGO possible, Rainer Weiss, Barry Barish, and Kip Thorne, received the Nobel Prize in Physics in 2017. And I think it is worth noting that Kip Thorne is the same physicist who lost the bet with Stephen Hawking about Cygnus X1. He spent decades working on gravitational waves, helping to design LIGO, and pushing through the skepticism and funding challenges that nearly killed the project multiple times. It took 40 years from the initial concept to the first detection. 40 years of persistence, ingenuity, and refusal to give up on an idea that many people said was impossible. That is the human story of black holes. Not just the physics, but the people, the stubbornness and the vision, the willingness to spend a career on something that might not pay off, and then the vindication, the moment when the signal comes through and you know that you have heard the universe singing in a frequency no one has ever heard before. And now, I want to bring you back to the quieter version of all this. Because we have been to the edge of the universe and inside event horizons and through the mathematics of space and time switching places. And now, I want to come back to where we started. To you, lying here, in the gentle gravity of a small planet, on a quiet night. One of the things I find most beautiful about this subject is the way it reframes the ordinary. Once you understand what space-time is, once you understand that the geometry of the universe determines what is space and what is time, the everyday world looks different. Not scary, just richer, more textured. The pull you feel right now, holding you against the mattress, is not a force. It is the Earth's mass curving the space-time around you. The bed is pushing you off the natural path through space-time, and that push is what you feel. If the bed disappeared, you would not fall. You would float, following the curve of space-time, weightless, the way astronauts do. The light from whatever lamp or screen is in the room is made of photons, massless particles that follow the curvature of space-time perfectly. They travel along what are called null geodesics, paths of zero space-time interval, which sounds technical, but really just means they travel at exactly the speed of light through space-time, always, under all conditions, no matter what the geometry is doing. And the time that is passing, the seconds ticking by as you listen, that time is slightly different at your head than at your feet. The clocks are ticking at different rates. The space-time around you is not flat. It is gently, imperceptibly curved. And that curvature is the same phenomenon, the very same physics, that inside a black hole becomes so extreme that space and time trade places. You are swimming in the same ocean that creates event horizons and singularities. You are just in the shallow end, And there is something profoundly comforting about that, I think. The laws that govern the most extreme and violent objects in the universe are the same laws that hold you in your bed right now. The universe has a unity to it. From the quantum foam at the Planck scale to the supermassive black holes at the centers of galaxies, it is all one physics, one geometry, one space-time. The differences are in degree, not in kind. Let me revisit our central idea one final time, because each time we circle back, we can see it from a new angle. Inside a black hole, space and time switch places. We have talked about what that means in the mathematics, the sign flip in the metric. We have talked about what it means for light cones. They tilt so far that the singularity is in your future, not in front of you. We have talked about what it means for your experience, the inevitability of the singularity, the uselessness of struggle. We have talked about what it means philosophically, the contingency of the space-time distinction, the idea that the categories we take as fixed are actually flexible. But there is one more angle I want to share with you, and it is perhaps the most mind-bending of all. Think about what it means for the nature of the singularity. In the Schwarzschild black hole, the singularity is a point of infinite curvature, and it sits at the center of the black hole. At least, that is how it looks from outside. But inside, where space and time have switched, the singularity is not at the center. It is in the future. And if the singularity is in the future, that means it has not happened yet. From the perspective of someone who has just crossed the event horizon, the singularity is coming, the way Tuesday is coming, the way the heat death of the universe is coming. It is a future event, and it is approaching you whether you do anything or not. And this means something extraordinary about what the inside of a black hole looks like. From outside, you might picture the interior as a fixed region of space, a sphere of weirdness sitting there in the universe. But from inside, the interior is not a fixed region of space. It is a span of time. The distance between the event horizon and the singularity is not really a distance. It is a duration. It is how much time you have left. The interior of a black hole is not a place. It is a time. And that, honestly, is one of the most profound things I know about the universe. The interior of a black hole is not a place you go. It is a time you pass through. And at the end of that time, at the moment of the singularity, something happens that we do not understand. Space-time curvature becomes infinite. The equations of general relativity fail, and whatever lies on the other side, if there is another side, is unknown. Some physicists speculate that the singularity might be resolved by quantum gravity into a bounce, where the collapsing matter rebounds and creates a new expanding region of space-time, a new universe, perhaps. The idea of cosmological natural selection, proposed by the physicist Lee Smolin, takes this even further, suggesting that each black hole in our universe might give birth to a new universe with slightly different physical constants, and that universes that produce more black holes are more successful in this cosmic evolutionary process. Is that true? Almost certainly not in its original form. But the idea captures something important. The singularity inside a black hole is not the end. It is a question. It is a place where our understanding fails, and where new understanding might begin. And this connects to a deeper pattern in the history of physics. Every time our theories have predicted a singularity, an infinity, a point where the math breaks down, it has turned out to be a sign that we were missing something. The ultraviolet catastrophe in classical electromagnetism, where the theory predicted infinite energy radiation from hot objects, was resolved by quantum mechanics. The infinities in quantum electrodynamics were tamed by the renormalization program of Feynman, Schwinger, and Tomonaga. Each singularity was not a dead end, but a doorway. The singularity inside a black hole may be the biggest doorway of all. It may be the place where general relativity and quantum mechanics are finally forced to merge, where the theory of quantum gravity is not a luxury, but a necessity. And whatever that theory turns out to be, it will tell us something profound about the nature of space, time, and the universe. And it will answer the question that has been quietly sitting at the heart of our conversation all evening. What does it really mean for space and time to switch places? Is it just a curiosity of the coordinate system? Or is it telling us something deep about the relationship between space and time? Something that we have only glimpsed and not yet fully grasped? I think it is the latter. I think the switching of space and time inside a black hole is a clue about the deeper nature of space-time, about the way it can reshape and reconfigure itself, about the way the categories that seem most permanent and most fundamental are actually malleable, contingent, and perhaps even emergent. And that brings us, finally, to the frontier, to the place where the questions are bigger than the answers, to the edge of what we know. We do not have a theory of quantum gravity. We do not know what replaces the singularity. We do not know whether information is truly preserved or how it escapes. We do not know whether the holographic principle applies to our universe. We do not know what dark energy is, or whether space-time is fundamental or emergent. But we know an extraordinary amount. We know that space-time is a dynamic, flexible fabric that curves in the presence of mass and energy. We know that this curvature is what we call gravity. We know that extreme curvature creates event horizons, one-way boundaries in the geometry of reality. We know that inside those boundaries, the roles of space and time reverse, and the singularity is not a place, but a destiny. We know that black holes have temperature and entropy, and obey thermodynamic laws. We know that they merge and produce gravitational waves that ripple across the cosmos. We know that they sit at the centers of galaxies and shape the evolution of the visible universe. And we know that they hold clues to the deepest mysteries in physics. All of this, every bit of it, came from human minds working on the curved geometry of space-time. From Einstein in his study in Berlin, from Schwarzschild in the trenches, from Chandrasekhar on a steamship, from Penrose at his desk, from Hawking in his wheelchair, from Bekenstein as a graduate student, from hundreds, thousands of physicists, mathematicians, astronomers, and engineers who contributed pieces to the puzzle over more than a century. And you, lying here, thinking about it, turning it over in your mind, that is part of the story too. Understanding is not a spectator sport. When you grasp, even for a moment, what it means for space and time to switch places inside a black hole, you are participating in one of the great adventures of human thought. So let's settle in with it. Let's let the strangeness be gentle. You are lying in the mild gravity of Earth, in a space-time that is barely curved, where space is reliably spatial, and time is reliably temporal, and everything behaves more or less the way you expect. But the same equations, the same geometry, the same physics, in more extreme conditions, produces regions where these familiar roles reverse, where the direction you must travel through becomes the direction you used to choose, and the direction you used to choose becomes the direction you must travel through. Space and time switch places, not in science fiction, not in metaphor, in the actual mathematics of the universe, in the geometry of space-time itself. And you exist in that geometry, right now. Every atom in your body is embedded in the four-dimensional fabric that Einstein described. The gentle curvature around you is produced by the same equations that produce event horizons and singularities. The time flowing through you right now carrying you into the future, is the same dimension that, inside a black hole, becomes something you can move around in. You are part of this story. You are made of space-time stuff. And space-time, it turns out, is far stranger, far more flexible, far more beautiful than anyone imagined until a century ago. That is a good thing to fall asleep thinking about, I think. Not the strangeness alone, but the beauty of it. The beauty of a universe that has these hidden depths. That looks one way on the surface. Gentle, predictable, familiar, but contains within its equations these astonishing possibilities. Black holes, event horizons, regions where the fundamental categories of reality rearrange themselves. And we found them, not by going there, but by thinking carefully, by writing equations and testing them, by pointing telescopes at the sky and listening for whispers in the gravitational waves, by arguing and doubting and checking each other's work and slowly, painstakingly, getting closer to the truth. The universe is under no obligation to be understandable. And yet, over and over, it turns out to be. Even its strangest features, even the places where space and time switch roles, yield to careful thought. Not completely, not yet. There is still so much we do not know. But the trajectory is clear. We are understanding more, not less, as time goes on. The mysteries are getting sharper, better defined, more precisely formulated, even when the answers remain elusive. And that is the note I want to leave you with tonight. Not an answer, but an appreciation. An appreciation for the universe that produced you, and that contains within itself these extraordinary structures. Black holes, where space and time swap their identities, where the singularity waits in the future, like a destination you cannot avoid, where information may be smeared across a surface, and the interior may be nothing more than a holographic projection. You live in that universe. You are made of its stuff. You follow its rules. And its rules are far more interesting than you might have guessed. So close your eyes, if they are not already closed. Feel the gentle pull of gravity, the curvature of space-time, holding you against the bed. Feel time flowing through you, carrying you into the future, second by gentle second. And know that this same physics, these same equations, in other conditions, produce the most extreme objects in the cosmos, objects where the very nature of space and time transforms. That is a wonderful thought to carry into sleep. The universe is strange, and we are part of its strangeness. The universe is beautiful, and we can see its beauty, even in the dark. Good night.